Okay, so we are starting this section of problem solving session for week 2 for the course Traffic Engineering, and my name is Tanu Singh, PMRF Scholar, Department of Civil Engineering from IIT Kanpur. So first I will start with summarizing the week 2 lecture, and then we will solve some of the practice questions which will help you solve the assignment 3. Okay. Assignment 3, side 2. So we are starting with traffic stream and variability. In the last lecture, we have discussed that there are different drivers and different vehicles in the road. Therefore, which have different behavior. The different drivers will have different behavior. They will have in different age group. They will react differently, and also the vehicle types. We will see different modalities of the road of the vehicles on the road. So these variability occur due to driver behavior, vehicle performance, or the road geometry and the environmental conditions. So for all the traffic engineers, therefore, must account for these variability whenever we are analyzing, designing, or planning to improve the traffic facilities. So example of the variability is, for example, whenever we had to cross an unsignalized intersection, a term gap acceptance plays important role, as this gap is different for different drivers. Therefore, this shows the variability, and all the traffic engineers must account for this variability whenever designing. As we all know, different people will react differently, and it should be efficiently available for all different kinds of drivers. So coming to the different traffic facilities, the traffic facilities are broadly classified into two types. First is uninterrupted flow facilities, and second is interrupted flow facilities. In uninterrupted flow facilities, there are no external interruptions to the traffic movement. That means vehicles are not forced to stop by signals, stop signs, or uncontrolled access. For example, in expressway or mid-block section of highway, these are the examples of the uninterrupted traffic flow facilities. Then here the main parameter is the speed, which is mainly influenced by interaction among vehicles themselves. The second type of traffic facilities is interrupted traffic facilities. Interruption that is being caused by the external control devices such as a signalized intersection, toll plaza, or stop signs. Urban streets and signalized intersection fall under these categories. And because vehicle must frequently stop and start, traffic behavior becomes more complex. Now we will go ahead with the traffic stream parameters. The traffic stream parameters are of two types. First is macroscopic parameters and second is microscopic. In macroscopic parameters, we describe traffic stream as a whole that is represented by a single value. For example, the parameter used are average speed, flow, or density. Whereas microscopic parameters focus on individual vehicles or pair of vehicles. These include individual speed of vehicle, its acceleration, headway between two vehicles. So these both the parameters, the macroscopic parameters as well as microscopic parameters, are important depending upon the level of analysis required. Now coming to the first parameter, that was here, as we have just seen, there is three parameters. First is speed, flow density, and in the microscopic parameters, there is an individual vehicle speed, headway, spacing. So we will go one by one to understand these parameters. So first one is speed. So speed is the most important traffic parameters, and it is the fundamental It measures traffic performance and is fundamental in road design and traffic simulations. Next, speed can be divided into two types. First is time mean speed and second is space mean speed. The time mean speed is the average speed of vehicles past a fixed point over a time is calculated as arithmetic, whereas space mean speed represents the vehicle over a road length and is calculated as harmonic speed. So time mean speed is this is a particular point, and whatever speed any of the vehicle passes through this point is measured as the time means speed, whereas space means speed is, for example, if this is the distance from here to here, so we will calculate for each of the vehicle what was the speed over this road length. So this is difference between the time means speed and space means speed. And always remember that space means speed is always less than the time mean speed, because here in time because lower speed vehicles occupy the roadway for the longer time. Therefore, space mean speed is always less than the time mean speed. Now coming to the speed and its variability distribution. So the vehicle speed is not constant and it varies differently in different ways. So first one is temporal. Temporal meaning speed changes with time and traffic volume. Whenever there is different time, you can see different speed. If the traffic volume is high, so the speed is low, and vice versa. Secondly, it varies spatially. Spatially means a speed can be at particular location can be different, and if we change the lane, then it's different. If we change the road geometry, the speed changes. So it also depends upon spatially what is the location. The third is the modality. Different vehicles have different speed. So these are different types of variations in the speed. Now coming to the speed distribution. So due to this variabilities, speed is best represented using statistical measures such as mean or standard deviations. The coefficient of variation helps quantify dispersion. In many cases, vehicle speed follows a normal distribution. Useful in these is traffic, which is the vehicle speed follows a normal distribution, which is useful traffic analysis and simulation models. So this was all about the speed. So speed, we understand that speed is important in traffic analysis and design, and it varies depending on temporal, spatial modalities, and mainly it follows the normal distribution. Now this next traffic parameter is traffic volume. So traffic volume refers to the number of vehicles passing a specific point on a road during a given time period. And please be careful that it is a point measurement. We are not measuring over a length of a period, but a fixed position. So, for example, this is the point that we are considering. So, the traffic volume is what is the definition? Is it's the number of vehicles passing a specific point on a roadway during a given period of time. For example, we are standing and we are at this point and we are standing for 1 hour. So we will count the number of vehicles that passes through this point of the road. So this is referred to as traffic volume. So it can be vehicles per hour, number of vehicles that has passed 1 hour, or it can be calculated as vehicles per day. So mainly these vehicle per hour is referring to a rate of flow, which is important whenever we are designing or we are calculating the capacity, whereas vehicles per day are mainly used for the planning purpose that calculates the total demand of the road. And mainly we always try, instead of continuously for 1 hour, we always try to count vehicles for shorter duration and then convert the count equivalent to the required time period. So mainly traffic volume data forms the foundation for traffic planning, capacity analysis, as well as the roadway design. So this is the traffic definition of the traffic volume. Remember, it is the number of vehicles that passes a given point during a given period of time. That is number of vehicles, that is measured as number of vehicles per hour. Now coming to the daily and hourly traffic measures. So one of the most important measure is AADT, that is annual average daily traffic. It is represented as average traffic volume over all 365 days of the year, and it captures seasonal variations such as difference between summer and winter. And in many of the projects, it is not possible to calculate the traffic measured for the entire year. In such cases, we use average daily traffic. Average daily traffic or ADT is calculated from counts taken over a limited number of days. It can be 1 week, 1 month, whatever is the required thing. And we also calculate the weekday traffic measures such as average weekday traffic when weekend traffic patterns are significantly different. When weekday and weekends traffic are different, we calculate, and if we want to get the weekday thing, so we only take the weekday only traffic averages. Now coming to the hourly volumes are very important because traffic demands is not uniform throughout the day. Especially in the peak hours, in the morning peak hours or in the evening peak hours of the during the office opening and closing time, the traffic is more as compared to the rest of the hour. Therefore, sometimes we calculate the traffic volumes on the hourly basis. It is considering the design mainly focuses on the peak hour traffic, and also the peak traffic is direction. Now coming to the design hourly volume and peak hour factor. As I have already mentioned that mainly ADT, that annual average daily traffic, is mainly considered for planning and road design, but that requires an estimate of peak hour factor. To obtain this, what we do, we calculate design hour volume. So design hour volume is derived from ADT, then K and D. So K is proportional of daily traffic in peak hour. In the peak hour of a day, what is the proportion of the daily traffic? And D is directional factor, means with what is the direction of the traffic. Means traffic can go this word also and this word also. What is the, so this D considers the directional factor. And therefore, traffic volume within a peak hour itself is not uniform. To account for this, like for this peak hour, like that as 60 minutes, the traffic flow is not uniform. To account for this, what do we take? It's the peak hour factor. So peak hour factor is defined as the ratio of hourly volume divided by 4 into peak of 15-minute flow within that hour. And it is practically range between 0.7 to 0.98. So, and whenever from this formula we get a lower peak hour factor, that will indicate that there is more fluctuation within an hour, and if it is closer to 1, that means that it is uniform. Simply, if it is uniform, then all 15 minutes, all 415 minutes will have same traffic. Therefore, when we take the ratio, it will be equal to 1. And their fluctuation is more, then it will be low. And typically the design hour is taken as the 30th hourly volume of the year. So whatever is the, we calculate ADT and then we check what is the 30th hourly volume, and according to that our design has been done. So that balances, we do not over design or under design. Therefore, this is the main thing that we consider, that is 30th hourly volume of the year, and that is typically between the range of 8 to 10% of the ADT. Okay, so this was all about the volume. Now coming to the next parameter, that is time headway. But before this, does anybody have any doubt? Okay, am I audible to everyone?
Yes.
Okay. Okay, so we are coming to the next parameter, that is time headway. So time headway is difference between the arrival of consecutive vehicles, that is front to front. Okay, so it is means if the vehicle, for example, if this is the vehicle and it passes a point, this is difference between arrival, and this is the, for example, this is the point where you are standing. This is the first vehicle that crosses. When this vehicle crosses and reaches some point here, then there will be some other vehicle that will be at this location. So the difference between the time difference between this, it's this. So the time difference between the this. So when first vehicle was crossing this point, we started our stopwatch. Then when the second vehicle reaches this point, then we again stop our stopwatch. So whatever is the time difference between arrival of two consecutive front to front. Front to front means this vehicle's first part and this vehicle first part, not the last or the rear part of the vehicle. So this is how the time headway is calculated. So this is the microscopic. Since we are talking about individual vehicles, the macroscopic parameters were when we are talking about the traffic stream as a whole. Now we are talking about the microscopic. When we are talking about the particular vehicles or pair of vehicles, then we are talking about the microscopic traffic parameters. Time headway is microscopic traffic parameter, and it is calculated as time difference between arrival of consecutive vehicles front to front. So so it can be also calculated as the occupancy time plus time gap between the vehicle. What do you mean by occupancy time? So when the first vehicle was here, the time occupancy time is how much time is taken by the first vehicle to cross this line. So it will be the length of the, it will be the occupancy type of the first vehicle plus the time gap. Time gap is only this much. So let me mention the time gap. So time gap is this. When it is the rear end of the first vehicle and the front end of the second vehicle. So this is calculated as a time gap. So an occupancy time is the time taken by the first vehicle to cross this point. So it is occupancy time plus time gap equals to headway. So headway is very important because it directly influences the traffic safety, road safety, and level of service. Means if the vehicles are very close, if time headway is very less, it means the vehicles are very close to each other. That means it is the jam condition, which indicates level of service is not good of that capacity. It also indicates driver behavior. Some driver take small time headway, whereas others may take large time headway while they are driving. And it also influences the passing, merging, and crossing operations.
तो फिर क्या क्या करोगे आप?
Okay, so now we have understood what is time headway. Now we'll understand what is time headway distribution. So time headway distribution is varies at different traffic condition. At low traffic volume, vehicles, if there is very low traffic, that means the time headway between two vehicles is more. So at low traffic, vehicles interact very little with each other. As a result, headway appear random. So headway is random and are well represented, and it is mainly represented by a negative exponential distribution. And when the traffic flow is very high. Very high means time between two vehicles is very low. So it is mainly a condition of the platoon, or it is a condition of a traffic jam. So in that cases, headway distribution are mainly approximated by a normal distribution. Now, third is the intermediate, that is in between the high and low traffic volume. That in that it is a mix of random and plateau behavior. So that is mainly represented by a distribution, Pearson type 3 distribution. So these are the three distribution. So does that mean? That means there is no single distribution that fits to all condition, like or high traffic or medium or low. We cannot fit using a single distribution. For each of the condition, we have three different distribution, that is negative for low, normal distribution for high, and Pearson type 3 for the intermediate. So this is all about the headway. Now we are going with the next traffic parameters, that is traffic density. So traffic density is defined as the number of vehicles per unit road length, that is defined by the vehicles per kilometer, and it is mainly important because it affects how freely driver can maneuver and how comfortable the traffic flow feels. It is so as defined by the definition, it says number of vehicles per unit road length. Okay, so it for example, if we are considering this as the 1 kilometer road length, so whatever is the number of vehicles in this particular road length is defined as the density. Okay, so this is the definition of the traffic density. So it is mainly, so it is measuring density is little tricky. You can do this by either taking a video at high vantage point and then checking what is the number of vehicles in that particular road length. So and there's another method, that is indirect method. In that, what we do, we calculate flow, we calculate speed, and then using the formula, we calculate density, that is K is equals to Q divided by V. Then there are main density levels. First is zero. If there is zero, means density is zero, then density zero is number of vehicles per unit road length is zero. It means there is no vehicles, that is empty road. Optimum is maximum throughout safe space. So maximum number of vehicles that can be present in the road, but as a safe distance, because that is optimum. And jam density is when all the vehicles are standing bumper to bumper, and that is a condition of traffic jam. So at that, the density is high and flow is zero. So this is the density, traffic density. Now qualitative density and occupancy. So density can be classified as low, medium, or high. So low density is when demand is less than capacity. Means when number of vehicles per unit kilometer of the road is less than whatever can be on that road, that is defined as the low density. In this condition, all vehicles are moving freely, so that is known as free flow, and it is a good service. Then coming to the medium. So medium is when it is approaching capacity, means maybe it can approach to capacity of the road, but and it can have a maximum throughput, and after that the speed drops, but flow is reaching to the maximum. And high density occurs when demand exceeds the capacity. Whenever the demand exceeds the capacity and there is a condition of stop and go, just like a jam density, then we say it is a high density. So, and here we are also defining a term known as occupancy. So this is a proportion of a time a detector is occupied by, it is a way we can calculate the density. It is calculated by occupancy. divided by VL plus DL. So VL is the average length of the vehicle and DL is the length of the detector. So this is the way we can calculate the density. It is practical because we can measure it using a sensor instead of trying to cover whole road visually, instead of counting the vehicle in the 1 kilometer of the road. So here we can use just a sensor detector that will help us to calculate the density of a particular road. And this formula converts the occupancy to density. Now coming to the microscopic measures that we have discussed. First was the uh, time headway. Time headway we have already discussed. It is a time gap between the consecutive vehicles. Then the spacing, time, it was the time gap, whereas the spacing is defined similarly, but it is a distance between consecutive vehicles front bumpers. So uh, as we can say that if this is the first vehicle and this is the second vehicle, so and we will also, so the time difference between these two vehicles front is called as time headway, whereas the distance, when we calculate in terms of the distance, then it is calculated as the spacing. So and this is the method in which we can calculate the from a macroscopic we can calculate the microscopic or vice versa. If the formula is k is equals to 1000 by s, the s is the spacing. So if we divide 1000 by s, we get the density. Q is equals to 3600 divided by h. H is the time headway and v is equals to q by k. So as we have already discussed, microscopic is individual vehicle behavior, whereas macroscopic is when we consider traffic stream as a whole. So it is important to understand because understanding individual vehicle behavior allow us to explain traffic, what is the behavior of whole traffic stream. Okay, so now we have already discussed about different traffic parameters, whether it is microscopic or macroscopic. Now we are coming to the fundamental traffic relationship. Okay, so as we have already looked into this formula where Q is equals to KV. So this is the fundamental equation of traffic. And with this will be coming frequently in the upcoming lectures. So therefore, please remember Q is equals to KV. Q is the traffic flow, or you can say traffic volume. K is traffic density and V is the speed. Okay. So flow versus density and speed. At we have already discussed at low density. Density we have taken as 3. See, whenever the density is low, that means low density means number of vehicles in 1 kilometer of road are less. That means all vehicles are moving at high speed and are moving freely. And the flow means flow is traffic volume. Traffic volume is defined as number of vehicle per unit time. So this will be less. When we are coming to the medium, then near capacity, here the flow will be maximum, but the speed will be begin to reduce. In jam density, flow is also equals to 0, speed is also equals to 0. No vehicles are moving. Then comes to a bottleneck effect. Bottleneck effect means whenever the uh, the construction work or something is happening on the road and there happens a condition when the road is being blocked, so that is known by a bottleneck effect. So in bottleneck effect, what happens if, for example, if this was the road and further some construction was happening in this area, so what happens? All the traffic will be moving from this. So whatever there was the traffic that was 4 lane, now it's been reduced to 1 lane. So in the upstream, so So this is the upstream. So upstream becomes unstable, and downstream flow is limited by a bottleneck. Whatever is the capacity of the bottleneck, it been limited by that, and upstream condition becomes unstable. Measurement locations, therefore, in this condition, if we are measuring traffic flow at this point, it will be different. If we are measuring traffic flow at this point, it will be different. If we are measuring traffic flow at this point, at a location here, then it will be something different. Therefore, sometimes this bottleneck effects comes with which in which the measurement is being affected for all the traffic parameters. Now coming to impact of measurement of the locations. So traffic measurements are highly location dependent, as I have already told you. It depends upon where we are calculating. So measuring at different points along the same road can yield very different speed low density. Maybe if we are calculating traffic flow after a signal, it will be different. If we are calculating before signal, then it will be different. See, the signal may define different measure, then bottleneck condition may happen, or there is locally demand something as is happening in the road infrastructure. So that may affect the observations. So for modeling validation, this matters a lot. You can just, so we can't just collect where and whenever we require the data to design or to do the analysis of the roadway capacity. So uh, so this is the example. If there is high-speed freeway, there will be wide range observation. If there is arterial, means the local road streams, then there will be discontinuous scattered data due to signals, because this is the interrupted flow facility, whereas this is the uninterrupted flow facilities. Therefore, the impact of measurement depends upon the uh, location. Okay, so whatever be the location, the traffic parameters may differ from one place to the other. So now coming to field data versus theoretical. So theoretically, it has been observed that VK, QK, and VK, these are the different fundamental equations of traffic. These are smooth and continuous. We will just see the graph after a few slides. So we observe that, but we have, as we have discussed, if there is high density, means traffic flow is, sorry, if there is low density, traffic flow is high, and vice versa, speed is high, traffic flow is less. So all these are smooth and continuous. But when we go on practical, then the free flow is often maintained initially. Initially, you can see that their free flow is maintained, but in the congested portion, it may be incomplete. Free flow speed may be unidentified, and in the parabolic shape from free flow to congestion, this we will discuss in the whenever we are discussing about the free flow condition traffic. So field so what happened, what we have found, that though it confirms a trend, it means that if there is low density, then the speed will be high. But theoretically, what we mentioned doesn't matches on the field what we see. So in these access control high speed roads, what happens? Driver tends to maintain speed aggressively until a breakdown occurs, and so up to capacity, speed reduction is minimum. Beyond capacity, speed gradually drops as queue forms, eventually reaching forced flow. And always remember that queue discharge flow is always below the capacity, but slowing is gradual, not abrupt. So traffic behavior depends upon road type, driver behavior, control features. This means when we calibrate models, we must consider road class, local condition, and just not rely on the theoretical curves. So what does this mean? This means that whenever we are calibrating any of the model, we must see as location differs, what are the local conditions, these or may differ, whatever we have considering. So theoretically in the field. So this we should keep in the mind. Now coming to the different regime models. So, what is the single? So first we will go in with the single regime model and then we will go to multi-regime. Single regime, what does it mean by single regime? So single regime means whenever in a traffic flow theory, what we describe, we takes the three equation, well, that is speed, flow, and density. So whenever to so in single regime is one in which a single mathematical relationship is used to describe the traffic behavior over entire range of flow condition, whether it is low, high, whatever is the flow condition, only one equation is required. Whereas the so the purpose is to understand the speed density flow relationship and estimate the capacity, jam density, and free flow speed. Single regime is one equation is required for all the traffic conditions. It includes both free flow condition and the congested condition. There are three classic models that are single regime. One is Green Shield, then Greenberg, and then Underwood. We will go one by one to all of these single regime traffic models. So first one is Green Shield. So Green Shield assumes a linear relationship between the speed and density. So its formula is V is equals to Vf minus Vf by Kj into K. So this is the equation. So first is speed versus density. This is the speed versus density diagram. So here the equation of this line is V is equals to Vf minus. So Vf is this. Free flow speed is defined as Vf. Kj is the jam density that is here. And what are the boundary conditions? Boundary conditions are when density is zero. Means density is zero. Means there is no vehicle. Then speed will be maximum, that is free flow speed. When K is equals to Kj, when density is equals to Kj, that is jam density, then the speed of vehicle is zero. Means in jam condition, all vehicles are standing, that is speed is equals to zero. So these are the boundary condition. Then flow becomes, whereas for flow, the equations, the graphs are parabolic. So this is the made diagram for between flow and density. So in this, as you can see, from here to here, it is defined as free flow condition till the maximum, and from there, this is known as the congested region. Okay, so this is the optimum density. Optimum density, and this portion is called optimum density, optimum speed, and optimum flow, or you can say maximum flow. So at Km is equals always equals to Kj by 2. Whatever is the jam density, it is always half. Then Vm is equals to, and the flow Vm here is Vf by 2. Whatever free flow speed is here, it will be Vf by 2. And Qm is equals to Vf into, and Q is equals to Kv. So it will be Kj into Vf by 2 cross 2 is 4. So this is the three fundamental diagram for green fields. These are the simple and it are most widely used. First one is speed versus density, then speed versus flow, and flow versus density. So this is, so you can see as this is density. As density increases, as the number of vehicles increases, flow increases, and speed also increases. And after a certain point, they will achieve an optimum thing. After that, if density increases, means number of vehicles are increasing on the road, but they are reaching a condition known as jam conditions. Therefore, whenever from here to here, the speed is being reduced and flow is also reducing, but density is increasing as it is reaching to jam conditions. So this is about green shield condition. Now coming to the next model, that is Greenberg's. First one was Green Shield, now it is Greenberg. So Greenberg's model assumes that there is a logarithmic relationship between speed and density. In this model, speed is expressed as log function of ratio of jam density to actual density. The formula is V is equals to Vm log of Kj by K. This model fits moderate to high density traffic conditions better than green shield. For medium to high density, it is mostly suitable as compared with green shield. However, limitation of Greenberg is that as density approaches zero, speed approaches infinity, which is not realistic in practical situation. Therefore, this model is generally not used for the low density or free flow condition, but it performs well in the congested traffic regimes. And here in the capacity condition, M is equals to Kj by E. In the green field, it was Kj by 2. Here it is Kj by E, and Vm is equals to speed at capacity. So its limitation is not applicable at low density. Now coming to the Underwood's. It is another important single regime model that assumes the relationship as an exponential between speed and density. This model was developed mainly to address the shortcomings of Greenberg's that was at low density. Here, speed decreases exponentially with increase in density, starting from the free flow. So in Underwood this performs work well in the low condition. Its formula is V is equals to Vf e to the power minus k by km. Even at high density, the speed never becomes exactly zero, which means it's not fully representative of traffic or jam condition. So why it is not applicable at high density? Because high density means coming to the jam condition. At jam condition, doesn't show that speed is zero. Therefore, it has this limitations. So it complements Greenberg's model behavior where that was not applicable at low density. This is applicable at low density. That was applicable at high density, and it has limitation in high density. This both complements each other. Now the comparison and interpretation. So in the green shield, what was happening? That speed versus density, the graph was touching both the axes. It was simple as an island. In a brick wall, what happens? It goes something like this. So in low density, what happens? It was achieving infinite speed. That was not possible. So that was limitation of Greenberg. Whereas in Underwood, it was something like this. Here, it was not touching the axis. Therefore, at high density, we were not getting exact zero speed at jam density. So it was realistic. So the green shield limitation, whenever we changes speed as with respect to density, we assume it has to be gradual, but it as a sudden, but sometimes a different uh, linear relationship, but it is not so impractical in the field. It is not a linear relationship. So therefore, for that condition, Greenberg and Underwood are working better, but Greenberg has limitation in low density, whereas the Underwood has limitation at high density. So, but all the three models have one thing in common, that is whenever this density is increasing, the speed is reducing. Okay, so now calibrations and takeaway. So these models are calibrated using the field data. We use all the field data to calibrate them. And this method for calibration are regression or least square method. The selection is based upon R square value and statistical significance. So what is the takeaway whenever we apply these models, these field data, we found there is no single model that fits all conditions. Model choice depends upon what is the road, what is the traffic, and what is the data range. Now coming to the multi-regime. Now the multi-regime, since one equation alone was not able to be applied to all the conditions, so therefore we are coming to the multi-regime. Multi-regime means more than one of the relationships are valid depending upon different traffic regimes. Means we can use more than one models depending on what is the condition. So in two regime models, we take two conditions. One is the free flow condition, another is the congested conditions. And if the model is three regime, then we consider three conditions. One is free flow, one is congested, and one is transition between free flow and congested. So there is one issue whenever we need to identify what is breakpoint, what is a point from where below which is the free flow or after is congested. So we need to point a particular point for these three models, like what is the range that we are considering for the three, two or three conditions. So now coming to the two regime models. So one of the most important, most well-known two regime model is the ADDIE two regime model. So here, what we take Underwood for free flow conditions, and it was not for it as Underwood was not able to represent the congested conditions. The reason was that Greenberg was poor at low density, whereas the Underwoods were poor at high density. So we have taken the mixture of both the things. For the free flow condition, we are taking Underwood, whereas for congested, Greenberg. The other two regime approaches are two green shade models, one for free flow and one for the congested conditions. And we also have the modified Greenberg model, where a constant speed in the free flow condition can be taken, and Greenberg model as it is in the congestion condition. So these are different types of two regime models. So a key limitation is that for all the two regime model is that speed values may not match at the breakpoint, causing discontinuity. Now coming to the three regime models. So three regime models have three equations, one for free flow, one for transition, and one for congested. And the advantage of three regime model is that better representation as gradual changes in traffic behavior, especially near the capacity. However, the main challenge is identifying two accurate breakpoints. In the two regime, we need one breakpoints, whereas in three regime, we need to determine two breakpoints. And again, there will be the mismatch of the speed at regime boundaries. That is the issue. So these were the three different types of regime models. Then the evaluation of multi-regime models. These fit observed free wave data better than a single regime, because it can be fit because we have at different conditions we have different models. These ADDIE performs slightly overestimates the maximum flow, whereas other models tends to underestimate capacity. Two regime linear models overestimate free flow speed, whereas modified Greenberg model underestimate the free flow speeds. So these are some of the observations of these model performance. Then all models significantly underestimate the jam density, and the three regime model underestimates the optimum density. So overall, there is no single model that works universally. Traffic behavior depends upon the road type, what is the traffic composition, what are different types of the vehicles on the road, what are the control conditions. So there can be different. So so main conclusion is mainly the model accuracy depends upon what is the roadway conditions. So this was all about the models and equations. Now we are starting with the interrupted flow. So interrupted flow where the traffic movement is being periodically stopped and released. Means we have the control where we can stop and release the traffic. So we are interrupting the traffic flow using external control devices. It mainly occurs that the signalized intersection or a stop and yield controlled intersection. So why this interruption is required? Because this is mainly required to improve the safety and efficiency, and also so that these conflicting movements at intersection can be served as a time sharings. Now, so what are the key characteristics? Key characteristics are that speed and density are not sufficient to describe the performance. Traffic operates in queue and platoons, and performance evaluated mainly using our delay measures. What are the so these are the different performance measuring parameters apart from the speed and density, that is queue, platoon, or what is the delay. Now coming to the key parameters in the interrupted flow. So at signalized intersection, when signal turns green, vehicle discharge from a queue. After a few vehicle, a constant headway is achieved. This is called saturation headway. Okay, so first, whenever the signal turns green, there will be a few time gap to for the first few vehicles to go, and after that there will be a constant headway between two vehicles. So that headway is called as the saturation headway. So when the signal changes, first we get the startup loss time, the time required to react to the change in the traffic light. Then there is clearance and end loss time, that is during amber and all red. So using this saturation flow rate, we define the we can calculate the saturation flow rate by 3600 divided by h. H is what h is the headway that we have already discussed. At unsignalized intersection, operation depends upon the gap. So unsignalized means we are not there is no traffic signals to operate the traffic. Therefore, all operation depends upon the perception of the gap acceptance. For some people, a same gap can be less, whereas for others it may not be acceptable. Some may reject that same gap, some may accept that gap depending upon their behavior, their driving experiences. So what is the critical gap? So critical gap is the minimum acceptable gap in major streets. Means that it is the gap that a driver is willing to accept, and it depends upon driver behavior, speed, and maneuver type, and also the road width. So because of these interruption, delay-based measures are used to evaluate interrupted flow facilities. So mainly how much delay is been. Therefore, instead of speed intensity for interrupted, we use a delay-based measure to calculate the performance of the interrupted flow facilities. So this was all about the summary of the week 2 lecture. Now we will go ahead with some of the practice questions. Does anybody have any doubt till here? Okay, so now we will start with the practice questions based upon the summary of the week 2 lecture of traffic engineering. For each of the questions, I will be waiting for around 2 minutes for all of you to answer this question. And after that, and you all can answer in the chat box, and after that, we will discuss the solution of each of the questions. Okay. So first question is, which of the following statement is false? First is time means speed is always greater than or equal to space means speed. B is time means speed will be equal to space means speed if variability speed becomes zero for any segment of load. Then C is F test is used as a test significant difference between means of any two sample of speed taken from same population. And D is coefficient of variation normalizes standard deviation. So the question is, which of the following statement is false? I will request everyone to answer the question in the chat box, whether your answer is correct or wrong. Please mention it in the chat box. At least try. Okay, so correct answer is C. That was answered by most of them. So first, so now we will discuss. So first statement is that the time mean speed is always greater than or equal to space mean speed. That is correct. Space means always less than. Then time mean speed will be equal to space mean speed. Okay, so time mean speed and will be equal if all the speeds of the vehicle are same, then both from the formula both time mean speed and space mean speed will come out to be equal. Therefore, this is also true. Then the D statement was coefficient of variation normalizes standard deviation. That is also correct. But the statement C, it was mentioned that F test is used to test significant difference between means for any two samples of speed taken from same population. That is false because F test is primarily used to compare variances, not the means of two samples. Therefore, to test the means of two samples, we can either use T test or ANOVA test. So therefore, the statement C is false. That was answered by most of the people. Now coming to the practice question number 2, that is which of the following statement are false regarding peak hour factor? Considering standard 15-minute analysis. So first, it is asked again which of the statement are false. So first statement is practical range for PHF lies between 0.5 and 0.88. Statement B is when there is no variation in flow within the hour, maximum theoretical PHF can be achieved. Statement C is if entirely hourly volume occurs in a single 15-minute interval, minimum theoretical PHF can be achieved, and D is theoretical minimum value of PHF can be seen. So I'm waiting for all of you to answer this question in the chat box. There can be more than one answer to this question. Okay, so yes, the correct answer is A and D because we have already, yeah, we have seen the practical range is between 0.7 to 0.98. So the first question is false. The second question is, the second statement says that if there is an uniform, there's no variation in flow within an hour, maximum theoretical PF can be achieved. That is false because the maximum value that we can achieve is 1, whereas the minimum PHF value is 0.25. So how it's 0.25, and say if entire hourly volume occurs in a single 15 minutes, then it will be the minimum. Okay, so yes. Okay. So this is the formula PHF is equals to hourly volume into 4 into maximum volume. It says if all the traffic volume occurs in that 15-minute thing, means that VF is equals to that maximum 15-minute thing. So this will be equals to 1 by 4, that is 0.25. So minimum value is that we can achieve is 0.25. So, and what it says and D says the theoretical minimum value of PHF can be 0. That is false. The maximum value that we can achieve is 1, and the minimum that we can achieve is 0.25. This is the range of maximum and minimum. So the correct, so the false statements are A and D. Because practical range is between 0.7 to 0.98, and theoretical minimum value is cannot be 0. Now coming to the next question, that is to calculate maximum flow of the road if flow speed relationship is given as Q is equal to 2.15 V minus 41 V log of V, where V is in kilometer per hour, where Q is in vehicle per hour. So we need to get the nearest integer value. Calculate, solve this numerical question, and write your answers in the integer in the chat box. And if you have any doubt regarding the previous questions, please let me know. I can explain it once more. Okay, so it is required to calculate the maximum flow of the road if flow relationship is given. So maximum flow what occurs at when dq by when you differentiate with respect to v, that is dq by dv is equals to 0. Okay, so now we differentiate q with respect to v. So what we get? So this 215v minus 41v into ln v. So what we get? dq by dv is equals to 215 minus 41 log of v plus 1. Okay, so then it's equals to 215 minus 41, and then we further derivate it. So we get it ln 41 ln v is equals to 174, and ln equals to 174 by 41, which is equals to 4.28 v, and we do antilog and we get it as 69.6 kilometer. Now to calculate the maximum flow, we write as Q max is equals to 215 and put the values of V in this equation, and we get, and the answer that we get is 2855. When we minus 1400 964 with 12109, we get it as 2855. So we're getting it around that, between 2852 to 2856. That is the correct answer. That can be a mathematical decimal equivalent to that. So now coming to the next question. Which of the following statement is false with respect to time headway distribution? So first one is negative exponential distribution closely matches with the measured time headway distribution when there is very little interaction between vehicles in traffic stream. Normal distribution closely matches with the measured time headway distribution at all levels of traffic flow. Pearson type 3 distribution closely matches with measured time headway distribution at flow near capacity. And then D is none of these. This we have already discussed while we were summarizing. All these questions are related to the time headway distribution that we have discussed. I will request everyone to answer the question. That might be correct or wrong, but it is a practice session. You will get to know, if you think of a particular answer, you get to know why that answer is correct or wrong. You're thinking it correctly or wrongly. Okay, so first let's go to the summary section where we have looked into the time headway distribution. So yeah. So what we have said that for low flow, negative exponential, for high flow, normal distribution, and for mixed, when we are moving from the uh, high to low between that condition, it's the Pearson. Okay. So what was the statement? Negative exponential says negative exponential. Negative exponential is for the low when the there is little interaction means there is the low flow. So that is correct. For negative exponential, we have seen that for low flow is the flow headway or low flow it is sorry low flow it is negative exponential. Now the option B was that normal distribution closely matches with the measured time headway distribution at all levels. That is wrong. It has mentioned as at all levels, which is a false statement. Now coming to the C statement that says Pearson type 3 distribution closely matches with the measured time headway at flow near capacity. That is correct because uh, that is the optimum flow. So that Pearson type 3 is the correct answer at high flow. Headways are skewed and the Pearson type skewed as well. So option number B, that is normal distribution closely matches with the measured headway at all level is false. So D can be because one of the statement is already false. So B is the correct answer. Now coming to the question. Next question that is if observed time headway is one way homogeneous traffic stream in is 6 seconds. The time headway is given as 6 seconds. Then which of the following describes the relationship between the space speed and distance headway? This is the questions. Try to solve this question. Time headway is given. We need to calculate the relationship between space mean speed v and distance headway. First thing, how is the distance? I have already explained the difference between the distance headway and time headway. Okay. Okay. So the answer is A. That is V is equals to 0.6 H. So, so the formula is H is equals to V into TH. H is the space means speed. V is equals to this H is the headway space, the space or distance headway. V is equals to speed in meter per second, whereas T is equals to time headway. So V will be equals to H by TH, which will be equals to H, and TH we have, it's been given the question is 6. And when we are converting, since it's been asked in kilometer per hour, we will be converting 1 meter per second, will be equals to 3.6 kilometer per hour. Therefore, V in kilometer per hour will be equals to H by 6 into 3.6. Therefore, we will get V is equals to 0.6 H. So the option A is the correct answer. Okay, so now coming to the next question, that is accept in terms of accept or reject. That is, congestion cannot occur at uninterrupted flow facilities. Answer to whether it is an acceptable statement or it is a reject. Okay, so the correct answer is reject. Why? Because uninterrupted traffic flow facilities. What does that mean? It's these are the flow. These are the facilities where traffic is not being stopped, not been stopped at intersection, or signals, or any of such as the free expressway or freeways. So on the expressway or freeways, the congestions uh, are not does not occur. Therefore, this statement is false. Therefore, we reject this statement that congestion cannot occur in at uninterrupted, because congestion can occur when firstly traffic volume is very much high than the capacity, and then there is an accident or bottleneck or lane reduction. Something happens, except for example, an accident happens and it closes the traffic, all the lanes, or there is a snow that closes all the traffic, then there will be the congestion for the all of the vehicles before that, or there is some maintenance happening, then there will be congestions. So these are the conditions where congestion can happen at uninterrupted flow facilities. So this statement is reject. Now coming to the next question, that is accept or reject the statement. Numerical check, graphical check, or chi-square test is conducted to select the appropriate mathematical distribution to the measured speed. Okay, so the correct answer is accept, because all these measured speed data is often being fitted to a probability distribution, and these all three method mentioned are used to select best fit distribution. That includes the numerical check, graphical check, and chi-square test or some statistical test. So these all three are correct. So we accept this statement. Now coming to the next question. That is, accept or reject the statement. Green shell model usually fails at both high and low density. Accept or reject. Okay. So let's since the questions in green about the green shield model, that it usually fails at both high and low density. First, let's see the green shield graph. So green shield, what says it says there is a linear relationship between speed and density. So it says it fails at both a low density and high density, which is false, because as we see from the graph, it says at low density speed is free flow speed. That is also correct, and at high density, speed is equals to zero. That is also correct, because that is the jam condition. So where does this green shield fail? So mainly green shield mainly fails at moderate to high, near around like this, because it says that there is a linear decrease in this speed, which is not exactly that is observed. The real speed flow curve is non-linear. So the statement it fails both at high and low is wrong, because it doesn't fail at low and high uh, density. It fulfills the observed condition. So the next question is, Addy's model usually unable to predict speed at low density. Accept or reject the statement. Okay. So it says about the eddies. Eddies come in the multiple region. So here the eddy 2 model for a free flow condition, we are taking the Underwood model, whereas for congested region, we are taking it Greenberg's model. Okay. So where we have studied about the model performance, we say that eddy has problem with slightly overestimating maximum flow. Okay, it doesn't have any problem in estimating the speed conditions. And as eddy is using the Underwoods in the free flow conditions, that is at low density, because Underwood is able to under because Underwood works well at the low density conditions. Therefore, the statement mentioned as the eddies model usually unable to predict speed at low density is false, because at low density traffic is free flowing and the most model including eddies predicts that speed is the free flow speed. And but the problem is eddies with the estimation of the maximum flow, and also at high density where there is a non-linear interaction dominates. Yes, the statement is false because it is able to predict speed reasonably at low density. The next question is, accept or reject Q discharge rate is always less than the capacity of undersaturated portion. Okay. So the last question is Q discharge rate is always less than the capacity of undersaturated portion. So the statement is A, that is accept. So what is this Q discharge? Q discharge rate is the rate at which vehicles leaves a queue at a signal. Okay. An undersaturated portion refers to a traffic when the traffic is arriving and it is arriving at a rate less than the capacity. So in the when the vehicles are arriving at less than the capacity, they are not delayed. But in practice, when a queue discharges, when a signal turns green, there is a loss, that is a startup delay, because first few vehicles take time to react and to the signal and then they accelerate. So there is always a delay when the queue is discharging. Therefore, average discharge rate of the queue is usually less than the maximum capacity of the approach. So under the traffic condition, it is always less than the capacity of undersaturated portion. Okay, so this statement is accept. As we have also discussed in the uninterrupted flow conditions, that there will be when there is a Q discharge, there will be a loss, that is startup loss time. So this was the some practice questions to help you solve the week 2 assignment. If there is any doubt regarding the session or regarding any question or any topic, please let me know. We can have a discussion on that. I will just summarize the today problem solving session, what we have gone through. Okay, so then we summarize the lecture. Okay, so first we started by saying there is a variability in traffic stream because of different types of driver, their behavior, different types of vehicles that can be found on the road, different types of road geometry. So there is always a variability in the traffic stream. Next, we have seen the different types of traffic facilities. There is uninterrupted flow facilities and there is an interrupted flow facilities. Whenever there is an external control, then the flow facility is interrupted, whereas where there is no external interruptions like signalized intersections or toll plaza, then there is whenever there is no such things, there is uninterrupted. So expressway or mid blocks of highway section are example of uninterrupted, whereas the signalized intersection, urban streets or toll plazas are the interrupted flow facilities. Then we have gone through the two traffic street parameters that can be a macroscopic parameters or microscopic. In macroscopic, we assume a traffic stream as a whole, which is represented by a whole traffic stream is represented by a single value that will be speed, flow, or density, whereas the microscopic parameters deals with the individual vehicles or pair of vehicles. Here we consider the individual vehicle speed or acceleration, there is time gap, and there is the distance gap. Then we have gone through what is about the speed. Speed is the fundamental traffic performance measure for the road design, for doing the analysis of fuel emissions, and also traffic simulation. Then we have discussed two types of average speeds, that is time mean speed and space mean speed. The time mean speed is average speed at point of a time, which is the arithmetic mean, whereas the space mean speed is average speed over a road length, that is harmonic speed. And space mean speed is always less than the time mean speed. Then we have gone through the speed variability. Speed can be varies depending upon temporal, time of the day, different locations, and also by different type of the vehicle. Different vehicle will have different speed. Some are slow moving vehicles, where some are fast moving vehicles. Then the speed distribution is often approximated as the normal distribution. Then we have looked through the different parameter, that is traffic volume. So traffic volume was number of vehicle passing through a point over a period of a time. It is always a point measurement. Like for whenever a vehicle passes through a point, we add it in the number of vehicles over a period of a time. It is measured in vehicles per hour or vehicles per day. And then its purpose is traffic planning, roadway design. We have seen different traffic measures. First, ADT is mainly for the designing purpose. And we have also seen the average annual daily traffic, weekday only traffic, and also discussed about the hourly volumes, because traffic show varies efficiently, and we can see the major traffics at morning and evening peak hours. Then we have looked into the design hour volumes, also peak hour factor. Design hour volume is defined as ADT K into D, where it has been taken as the 30th highest hourly volume. And we are taking 30th to balance economy as well as the efficiency. Then we have looked into what is peak hour factor. Peak hour factor is hourly volume divided by 4 into maximum 15-minute volume. Its practical range was 0.7 to 0.98. Then we looked into time headway. The time headway was the time difference between the arrival of two consecutive vehicles. And whereas the space headway is distance between the arrival of two vehicles. Please remember, it is always front to front, not the both for the both of the vehicle. It is always front of first, whereas front of back, not the back of the first and front. No, it's always front to front. And it comes under the microscopy because now we are talking about the particular vehicle. So these are mainly calculated to learn the driver behavior and also the passing, merging, and crossing operations. Then we have looked into the distributions. So for the low flow, it was negative exponential. For high flow, it was normal distribution. Whereas for the intermediate, it was best modeled by a Pearson type 3. And we have found that there was no single distribution that fits all flow conditions. Then we had looked into the other parameter, that was traffic density. So traffic density was the number of vehicles per unit road length. And it was important to understand the driver maneuverability and discomfort. It directly affects the traffic flow quality. So it can be directly measured by standing at a vantage point, recording a video, whereas indirectly it can be calculated using the formula K is equals to Q by V. We have seen different levels. If traffic density is 0, it means empty road. If it is maximum, then it is a jam condition. Then we have also seen how to calculate density using the occupancy using a sensor-based method. So, so the formula used was K is equals to OC by VL plus DL, that is average length of the vehicle plus the length of the detector. So this method was used because it was easy to measure. Then looking into the road of 1 kilometer and calculating the number of vehicles in that particular road length. Then we have seen how to convert the microscopic to microscopic. So these time gap and distance gap can be calculated to density and flow. Density can be calculated by 1000 by space headway, whereas flow can be calculated by 3600 divided by h. And V is calculated by Q by K. So this was all about the microscopic and macroscopic parameters. Then we have gone to the fundamental relationship between the these three, that is flow density and speed, Q is equals to kV. We have seen that at low density there is free flow conditions. At gap density there is condition where flow is zero and speed is also zero. And but there is also a condition that is bottleneck that might affect these things. There might be a condition where the upstream and downstream become unstable and they are limited by the bottleneck conditions. Then we have seen that the location where we are measuring these parameters may affect their values depending upon the bottlenecks, signal condition, or the local demand. So these validation depends where and when we have collected the data. Then we have seen the field data versus theoretically. It finds if we have find the field data confirms the trend, but it clearly matches the theoretical value. As theoretically, we assume all these VK, QK, and KV relationships are smooth and continuous, but that are not so in the field data observation. Similarly, in the modern freeway characteristics, it was like driver maintains speed until breakdown, then there is a minimal reduction to capacity, but the speed drops after the capacity. So traffic behavior depends upon what is the road type, driver behavior, and control measures. Then we have seen different types of the regimes. First one was the single regime. Single regime means only one equation is being used to define all the traffic flow conditions. Mainly the parameters were the speed, density, and flow. So there were three models. First one was Green Shield, then Greenberg and Underwood. Green Shield assumes a linear relationship between the speed and density, whereas for flow it assumes the parabolic. This was the equation V is equals to Vf minus Vf by Kj by K. These were the boundary conditions where when K density is zero, flow is maximum, free flow when density is jam density and speed is zero. So these are the conditions for the capacity, and since it is simple and practical, so it is widely used. Then we come to the Greenbergs because it been assumed that the relationship after moderate to height is not seen as the linear. So for this we have limitations. We have gone to the Greenberg's model. Greenberg's assumes the log relationship between the speed and density. It was this equation was this, and though it was suitable for the high density conditions, but in this the speed becomes infinite when density is zero. Yeah. So that was its limitations in the low density conditions. Then to resolve this, Underwood model assumes the exponential speed density relationship. This was the equation used in the Underwoods. It was working well at low density, but speed was not coming to zero at high density or jam conditions. So this was the limitation of this method. So if we compare, then Green assume touches both speed and density axis, but is assumes as linear, whereas Greenberg's it has no finite free flow at condition. Therefore, Underwood has zero speed at jam conditions. So therefore, these they was acceptable at low density, but these were acceptable at it was not acceptable at jam densities. So, but we had found that all these models show one trend, that was if we increase the density, then this speed is reduced. Then we have seen the calibration. These were different methods where model is being calibrated using regression or least square fittings. Then we have come to multi-regime because there was no uh, a model that was able to reflect the field data completely. So we are coming to multi-regime that uses different relationship at different conditions. Two regime for two conditions, three regime for three transitional congested condition. But the main issue was to calculate the breaking points where these conditions breaks, which is the breaking point for these two conditions. For two regime, we have the eddies, which assumes Underwood for low density whereas Greenberg for high density. The other two was two green shield linear equation. One another was modified Greenberg with constant speed at free flow and Greenberg modeling congestion. Then three regime models were used, but the limitation was that we need to calculate two breaking points for three conditions. Then these were the performance evaluated from these multi-regime models. Then we have come to the interrupted flow. Interrupted flow where the traffic movement is interrupted using external devices such as signalized intersection or stop and controlled or yield controlled intersections. Mainly it was interruption is been done to decrease the conflictive movement of the vehicles. So what we have found that speed and density are not sufficient to describe performance. Where traffic operates in queue and plateaus, therefore the delay based measured is will be best to calculate its performance. So the key parameters interrupted flow for signalized was saturation headway, loss time, and saturation flow headway can be calculated by 3600 divided by h, that is headway, and unsignalized and for unsignalized section, it really depends upon gap's acceptance. Critical gap is the minimum acceptable gap by a driver, and it is mainly influenced by speed, maneuver type, and road width. So this was the summary of this week 2 that we have discussed today. I hope there is no doubt with today's session. If you have any doubt, please let me know, else we will end this session. Okay, so I hope there is no doubt. So that's all for today's session. We will meet next week with another problem solving session for week 3. Thank you, everyone.